Okay, please start, Professor Lomonaco.
Oh, thanks. Thanks for the opportunity to speak here today. It's indeed a pleasure. There's so many great speakers at this conference. I'm enjoying watching many of the talks, as many as I can. Um, so the title of this talk is How to Build a Device That Cannot Be Built. And um, um, so this is the title itself. It simply means that the device cannot be built using classical physics, but can be built using quantum mechanics. And it leads to some interesting questions, at least for me, that is. The PowerPoint slides for this talk can be found on my website. Um, uh, this talk is based on the following paper that appeared in the Journal of Quantum Information Processing. It can also be found on the archive, but it's public domain. You can simply go to the website for Springer to get get a download of the paper itself, which in turn, gee, I can't read the top of my screen, is based on the following papers. The first is by David Mermin, Quantum Mysteries Revisited. The second is by Greenberger, Horn, and Zeilinger. I recommend these papers. They're interesting reading. I'd like to begin with a question, if I may. And the question is, what is the meaning of quantum mechanics? And if you'd like to have some fun, simply attend a physics meeting, find a group of friendly physicists, and ask this particular question. What is the meaning of quantum mechanics? Immediately, a very entertaining thing occurs when you make the statement. Lots of excitement occurs, and it's very entertaining. I recommend it for all. The dilemma, I can't see the top of my slides. That's one of the problems I'm having here. Let me see if I can. Um, ah, I have another way around it. Okay, this is our dilemma. There is no consensus as to what the meaning of quantum mechanics is. And the dilemma is the following, or this is the classic physics conundrum. There is almost universal agreement in regard to the laws of quantum mechanics. On the other hand, but there's almost total disagreement as to their interpretation. And there are many interpretations that can be found in the literature in this particular area. There's the Copenhagen interpretation. There's the many worlds interpretation. There's the consistent histories interpretation. There's the ensemble statistical interpretation. And it goes on and on. It's amazing the number of different models or interpretations of quantum mechanics that have come forth. The one I like the most, though, is called the Irish pub interpretation, invented by Jonathan Dowling. And essentially, it's the following. After zero beers, clear as mud. After one beer, somewhat clear. After two beers, very clear. And after three beers, it's obvious. After four, it's puzzling. And by this time, after the fifth beer, you're flat on your back and it makes utter nonsense. So essentially, what is the problem? What is quantum mechanics actually trying to tell us? Heisenberg's uncertainty principle says that simultaneous measurement of incompatible observables to unlimited precision is simply not possible. Then comes along Bell's inequality and simply says that one of two possible principles must be violated. The principle of reality, what you're measuring is actually exists before you measure it, And the second is the principle of locality, that is, space-time, space-like separated regions of space-time are physically independent of one another. These are regions of space-time for which communication can only occur faster than the speed of light, which is not possible. There's a Koch-Specker theorem, which is an interesting, don't have time to go into it. And the last one I'd like to mention is I think one of the most recent ones is the Conway-Koch free will theorem, which essentially says the past does not determine the future. It has nothing with to do with free will. It's unlike, it says quantum mechanics is unlike classical mechanics. Complete knowledge of the past does not determine the future. Now, the objective of this talk is to investigate the Greenberger-Horn-Zeilinger GHZ paradox using the tools of quantum information science and to push this investigation to its limits. One result, and I'll explain this in greater detail later, is that the second elementary symmetric Boolean function, sigma 2, can be interpreted as a quantification of the non-locality and or indeterminism involved in the GHZ paradox. You could think of it as an algebraic obstruction. We also illustrate the subtlety of distributed control of distributed quantum systems. You can control systems in subtle ways with quantum entanglement. Okay, let's go back to our problem. Our conundrum, I guess I'd like to call it. And this is a tale of three regions in space-time. I'd like to tell it as a story, if I may. Interstage right, supervisor, who bellows, build this physical system ASAP or else. Very, very dictatorial guy. And immediately puts down the following blueprint of a system he'd like to build. It consists of a source, which ejects objects, and detectors that once received detect the objects. And let's look at these. The detectors have a red light and a green light, and they have a switch. Upon it, a switch which can be set either to 0 or 1. Upon encountering a particle, the detector flashes either red, standing for 1, or green, standing for 0. Each detector has a switch I mentioned earlier, which is either 0 and 1, and you can randomly flip it back and forth anytime before the particle arrives. It doesn't matter. The source essentially contains 3 particles and a small blue button, which when pressed ejects the particles all at once toward their respective detectors. And there's our blue button. And maybe it flashes too much, I don't know. The supervisor is only interested in the switch settings for which an odd number of the 3 switches is set to 1. That is, if we have switches A, B, and C, one switch setting would be 0 for A, 0 for B, 1 for C. And here are the other switch settings. And now we've seen all possible odd switch settings of Hamming weight 1, and there's an additional one of Hamming weight 3. No other switch settings are important in the design of this system. The supervisor doesn't care about the remaining 4 settings. And then there's specifications that must be used in designing the system. The first spec is that for switch settings of Hamming weight 1, after 3 particles received, only an odd number of detectors flash red. It's amazing how concrete this is, yet it cannot be constructed classically. Specification 2, for the switch setting of Hamming weight 3, after all particles received, only an even number of detectors will actually flash their lights red, 1. And there are constraints. First constraints, detectors cannot communicate with one another. They are actually separated by a space-like distance and hence physically independent of one another. Constraint 2, upon leaving the source, the particles can no longer communicate with one another. Constraint 3, each particle only communicates with the detector when it encounters the detector. So the supervisor leaves with an ominous command: build this system ASAP. He's really pushing his employees, isn't he? And enter stage right, of course, a design engineer is called in to actually implement the design or show how to implement the design. After analyzing the system, he comes up with the following logical arguments: since detectors cannot communicate, since after injection particles cannot communicate, and since particles only communicate with the detector on impact, there's only one conclusion that can be made: each particle must carry the instructions for the detector, what the detector should do. And then he begins to look at this last condition, or mathematically. And well, this is actually here are the instructions for particle A, essentially a function from the set 1, 2 to 2 chosen colors. And then the instructions for particle B are simply a mapping from 1 and 2 to the colors 1B and 2B, which you can choose either red or green for each, and so forth. All right. Thus, particle A must carry instruction, which is a function which maps switch settings to colors or Boolean functions of the form. Essentially, for each particular switch setting, which is either 0 or 1, it produces a color instruction for the detector, where red stands for 1 and green stands for 0. Okay. In like manner, the remaining 2 particles must carry Boolean function instructions. So I denote those by F sub B and F sub C. Thus, for A, B, and C, each instruction is simply a Boolean function from the set of 0 and 1 into the set of 0 and 1. Very simple, very simplistic system. Spec 1, let's take a look at our specs and see what it says about these Boolean functions. For the switch settings of Hamming weight 1, after all 3 particles received, only an odd number of detectors flash red. Specification 2, for switch setting of Hamming weight 3, only an even number of detectors must flash red. And so we can say this in terms of Boolean equations. Here we're doing 0 and 1 mod 2, and the first specification says for particle that the switches must satisfy the top 3 equations. The last spec says that they must satisfy the bottom equation. But now we have a problem. We've expressed our constraints in terms of a system of Boolean equations, 4 equations and 3 unknowns. And unfortunately, the system of linear equations is obviously inconsistent, I said. I mean, inconsistent. And that, if you can see that very clearly, if you add the first 3 equations, you end up with a linear equation, which is inconsistent with the bottom equation. Ergo, the only solution you can make, according to the design engineer, is it can't be built. This defies logic. It's just not possible. At this point, someone very important appears. That is Interstage Wright, a quantum computer scientist. Thankfully, the day is saved, I think. I'm making this a story, but anyway. Begins to analyze the system. He says the following. Let the three particles in the source be photons in the entangled state is given here. This is ket notation. If we look at the first ket, the leftmost ket is in state 0. Let's see, you can't, I don't know, can you see my pointer? I'm not sure if anyone can see. Let me create a pointer that people can see. Pointer options. Here it is. Here's my so the left qubit is in state 0, the middle in state 0, and the right in state beta. This is the state ket 0, 0, 0. And here are the other three states, and this is a linear combination. This particle is in a superposition of each of these states. All right. And the next thing we do is where 0 denotes, we need to implement this physically, represents a horizontally polarized state, and ket 1, denotes a vertically polarized state. All right, should be familiar with this. We all use polarized sunglasses. The light from the road is, when you're driving, is polarized. I believe it's horizontally polarized, so your glasses filter that out and receive only the vertically polarized light. I hope I haven't got it reversed, and in which case it eliminates the glare. There's more that can be said about this, but I'll go on. Please note that this entangled state is entangled. You can't factor it into the tensor product of three separate states. Stated physically, you can see that the state of the left qubit is indeterminate. It's neither 0 nor 1, can't simply be defined. The middle qubit is simply indeterminate. Its state is not known. And the same is true of the right qubit. And the state of each qubit individually is not defined, indeterminate. The state of all three together is well defined. This is one of the properties of quantum entanglement and one of the mysteries of quantum entanglement, I guess. The state of each qubit is indeterminate, but the state of all three is well defined. Now let's take a look at our detectors, and what the design engineer decides to do is he inserts what we call a Hadamard transform at switch setting 1. And the other simply is the identity unitary transformation. And the Hadamard transformation is a qubit. The state of a qubit is a vector in a two-dimensional Hilbert space. And the actions on qubits are unitary transformations. The Hadamard transform is a unitary transformation lying in the special unitary group SU2. And so we'll implement this. This can be easily implemented in optics on an optical workbench. Okay, hence, what happens? Well, this is the definition of the Hadamard transform. It transforms ket 0 into what we frequently call ket plus in quantum computing, and ket 1 into ket minus as a shorthand name for the linear combination. So it forms that linear transformation, and it acts on each of the basis elements, 4 basis elements, which are labeled each by 3 bits in linear superposition. Let's go on. Now I'd like to just be a little technical, I guess. A Boolean unitary transformation is a map from, maybe I'll simply say this very simply. It's simply a Hermitian, essentially an operator, a unitary or Hermitian operator that's controlled by classical bits. And let me show you what I mean. If B is either 0 or 1 and U is a unitary, we'll simply denote U sub B to note the following Boolean transformation. If the Boolean value is 0, it's simply the identity transformation. If the Boolean value is 1, it's a unitary transformation U. We can do the same thing with observables, where I is the identity operator. We can do the same thing with observables, Hermitian operators. Omega is an observable. Then we can turn it into a Boolean observable. When B is 0, then it is the 2 by 2 0 Hermitian operator. And when B is 1, it's the Hermitian operator omega. We're going to use these things because we'd like to show how to design a system that cannot be built. And we usually use wiring diagrams in quantum computing. There's a very good reason for using wiring diagrams. They represent unitary transformations. And the problem with the unitary transformations in quantum mechanics, they grow exponentially large very quickly with a number of qubits. Unfortunately, wiring diagrams grow linearly with a number of qubits. So we can represent these exponentially large matrices in terms of very compact wiring diagrams. So let's go to the next slide. Here's an example of a wiring diagram. Each line in the wiring diagram represents a qubit in time. This first line is the first qubit. At the input, the bit is initially prepared in the state ket 0, and the remaining 2 qubits for the different qubit 2 and qubit 3 are each set to be in the initial state of ket 0. And as time goes on, each of these little boxes and symbols here represent the application of different unitary or transformations to the qubit. You can see that first a Hadamard transform is applied, and I'll explain, and we've seen that already. Then a controlled NOT transformation is applied. So this changes the state, flips the state of the target qubit if the state of the top qubit is a 1 and leaves it alone otherwise. Here's another controlled NOT where the top qubit controls the bottom qubit. U is a unitary transformation, which I'll show you in a second. At this point, we can see that the first part of this diagram is simply preparing a given state. We simply put the 3 qubits, initial qubits, transform them into 3 qubits in this particular entangled state. The next part of the diagram, essentially, we have switch settings, and we use that to control. Either we apply a Hadamard or we don't, depending on the Boolean value of each S. For instance, S1 is 0 or 1. If S1 is a 1, nothing is done. If S1 is a 0, something is done. This is the opposite of the black dot, which represents control. Essentially, 1 makes the change for a black dot. A hollow black dot, I guess you'd call it that, changes only when the qubit is in the opposite state, 0. And so after these Hadamard transforms are applied by the controls, a measurement is made with respect to the Pauli spin operator Z, which is okay. And let me see what I can do here. So let's take a look at some of these. Single lines represent qubits, and double lines represent classical bits. This represents a control knot. I mentioned that earlier. Um, it makes a change if the top qubit is a 1, it flips the bit, and otherwise it does nothing. And it has a corresponding unitary matrix as so shown. Okay, and this denotes a measurement with respect to the standard basis, ket 0 and ket 1. This is a measurement with respect to the Pauli spin operator. I forgot to put the matrix in that, but it's a 2 by 2. If anyone wants to know, we can define these matrices later. But essentially, besides being unitary, it's also Hermitian. So we're actually using it to make a measurement. And I also forgot to mention that double lines denote classical bits, solid lines denote quantum bits in these diagrams. So after the measurement, you produce a bit, as you will see, or an eigenvalue, as being very precise. And it has become classical because we have measured it. So, and this is the other controlled Hermitian operator, not Hermitian, unitary operator, the Hadamard transform. The star denotes complementation of the bit. So when you apply this operator H, when the switch is set to 1, and you do not apply it when the switch is set to 0. I believe that's what's all right. And let's see what we have. Here is the unitary operator U. It notes the following unitary gate, simply the exponential of linear combination of the Pauli spin operators. And I wrote it down explicitly. I think there's a typo in here. I think that's a minus. I'm not sure. I have to go make the calculations. In any case, it's a well-defined element of SU2. Its determinant is +1. Right? Where X, Y, and Z are the Pauli spin operators. Let's go back to the diagram. Now I think hopefully it's a little more understandable. We have the initialization. We prepare the qubits initially, all in state 0, ket 0, and then we have the preparation phase. This is all one big unitary operator. Actually, an 8 by 8 matrix, if you like to look at that. And then we have the switch settings and the measurement. Okay. And now let's take a look at this. Okay. Oops. Excuse me. Just trying to do a few things here. All right. So we can simplify the diagram a little bit for analysis by using the following measurement gate, which is equivalent, as we will see. I denote it by these symbols, and here's the definition. Essentially, it's the Pauli spin operator if the switch setting is 0. It's operator X if the switch setting is 0. Operator Z, which is also the third Pauli spin operator when the switch setting is 1. And I'm not going into details how it collapses into that, but it's a very simple exercise. Okay, here it is again. Everything is simplified. And now you can see that how this wiring diagram brings out the structure of the functions carried by the qubits, the F sub A, S1, and so forth, supposedly carried by them. All right. And we have the source and the detectors. And let's see what this is all about. I have a little table here. Essentially, here are the switch. This column represents the 3 switch settings, and this represents the results after the controlled Hadamard transforms are applied. It's either it does something if the S's are have a certain value, it does something else as the other value. All right, if we take the switch settings of Hamming weight 3, then the result is the following entangled state. And you can see that all cats are labeled by binary strings of Hamming weight 2, of even Hamming weight, excuse me, of even Hamming weight in this case. And now let's take the switch settings of Hamming weight 1. In this case, it's a linear combination of cats labeled by strings of length, binary strings, which consisting of 1, of Hamming weight 1. And the same is true for all the other Hamming weight 1 switch settings. They lead to linear combinations of Hamming weight, of odd Hamming weights. I think you can see by now where this is leading. What do the 3 detectors see for switch setting 3? Let's take a look at it. If we measure each individual qubit at this time, suddenly, with probability of half, either we'll see 0, 0, 0, 0, an even number of even Hamming weight, another even Hamming weight. Each time we make a measurement, we end up with a switch setting of even Hamming weight, each occurring with probability of 1/4. In one sense, we can't control the outcome of a quantum measurement. All we can do is control the probabilities. So this produces a switch, basically the instruction 0, 0, 0. This produces which is green, 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 and so forth. All are a even number of reds and odd number of greens. It's amazing how this is done. Therefore, always an even number of reds occur in this particular state as per the specifications. For odd things, for settings of odd Hamming weight not for odd Hamming weight, for Hamming weight 1, we have the following occurs. We can make the measurements, each occurring, there are 4 possible outcomes, each occurring with probability of 4th, but in any case, there are always an odd number of ones in each of the outcomes. They're of odd Hamming weight, so the result is always an even number of greens and an odd number of reds, depending on how you look at it. Therefore, always an odd number of reds. Okay. So the question is, we've actually constructed the device, but we gave a very cogent proof. So what happened with our proof of impossibility? Where did it go awry? The proof of impossibility is based on the following proposition. There exists no set of Boolean functions such that the following set of equations, or the following linear combinations satisfies these conditions. This is one way of satisfying all 4 equations. This is perfectly elementary, simple argument. It has to be true. It has to be true. So what went wrong? The logic is actually flawless. But the crux of the matter is that an argument is only as sound as the assumptions upon which it is based. More explicitly, the argument, what should I say? The argument, excuse me, part of my slide is hidden here. The argument fails because at least one of the following tacitly assumed two assumptions fails. These are the assumptions which are seem to be perfectly obvious assumptions. The first is the reality principle. What is measured is completely determined before it's measured. And the other premise is the principle of locality. Space-like separated regions of space-time are simply physically independent. There's no way to communicate between them. There's no way to communicate between the detectors. So it leads to the following. These two assumptions lead to the following unfounded conclusion. Based on premise one, the reality principle, the detector lamp instructions, FA, FB, FC, must already be predetermined, well-defined total functions at the time of particle ejection. Unfounded conclusion two, based on premise two, the principle of locality, the detector lamp instructions must be local. Hence, f sub j is a function only of the jth switch setting, Sj, independent of the two other switch settings on the other detectors. So essentially, at least one of these two principles must be violated. Corollary, the switch settings of odd Hamming detector lamp instructions, okay, are random. They're actually partial functions. They're never fully defined. Depends on, and they're defined in a different way with each particular measurement. And they are given by essentially, they're constrained, although the switches have to be physically independent, they're constrained by the following Boolean function. So the quantum mechanical system has created three space-time separated regions of space in which we have constructed three probability distributions, which should be independent of one another, but they're not. They're actually dependent probability distributions. Sigma 2 denotes the second elementary symmetric function. It's a simple Boolean function where plus denotes exclusive OR, and the assumed dot between S1 and S2 is logical AND, or multiplication, if you'd like to call it that. In other words, the GHZ paradox, shows how to create three space-like separated, hence physically independent probability distributions that somehow have an algebraic dependence. This is perplexing. The Boolean function sigma 2 quantifies the non-locality of the GHZ state. And that's the end. I'm also selling quantum wiring diagram kits if anyone's interested. And I would like to thank all of you. It's been fun giving the talk, and I'm open for any questions you might have.
Thank you.